Hi, my name's Dan, and this video is one in a quite large sequence of videos which is charting the progress of creating a 4-bit CPU from basic logic gates. I'm doing it using a simulator rather than using hardware. That simulator is called DigitalWorks, and there is a link to it in the description below, but we're not going to see it in this video. And a roadmap of where we're going in the grand scheme of these videos is also down there in the description below. And at this point where we're spending a bit of time over a smaller set of videos thinking about the design of the CPU, the elements that are going to go into it, and how we're going to realize it. And we've got to the point where we need to talk about the fetch execute cycle. So we've hinted stuff about this, or talked a little bit about it in previous videos, but I'm going to go through the cycle that the CPU needs to go through in order to process a set of sequential instructions. So it needs to get an instruction from the memory, and then it needs to carry out that instruction, and then it needs to increment the program counter. And if you've been following along, you'll know that we have a special register called PC, which is the program counter, which keeps track of where we're up to in the program. Okay. So technically, this could be called the fetch-execute-increment cycle. There are other descriptions and other ways of approaching this a bit. So I've seen fetch-decode-execute, where you spend one clock cycle decoding your instruction and then executing. The hardware that we've got is not so complicated that we need to do the decoding as a separate thing. And we're going to approach this in a particular way. Okay, so in fact, I've got to say at this point that there are loads of different ways of designing CPUs and loads of different ways of implementing this sequence, and there are nuances to it that we're not really getting into in this because I'm taking quite a ham-fisted approach to the whole design, so that it's A, relatively easy to design, and B, fairly easy to implement in a synthetic way in our simulator. So where were we? Going to get the instruction from the memory. So in order to do that, we need to take the contents of the program counter and put it in the memory address register, and then we need to read from the memory, which will take the relevant piece of information from the memory into the memory data register, and then we need to copy the memory data register into the op register, which is where it's going to be interpreted. Okay, so what I'm going to do at the moment is I'm going to ignore the fact that some of the operations have extra data associated with them, because this adds a complexity to this fetch execute cycle that I don't want to deal with right now. And also I have a trick for this, but I haven't talked about it yet, and I want to do that in the next video, talking about how I'm going to solve that problem. So I'm not going to solve it by having extra cycles or extra parts of the this sequence in. You'll see. Come back. That's a cliffhanger if there ever was one. Okay. So in register transfer language, if you're used to that, then the indications for this are you're going to read the MAR from the PC, and then you're going to read from memory, and then you're going to read the op from the MDR. Number 2 in this doesn't need the bus, because it's reading from memory has got its own internal bus. So actually, we are able to do numbers 1 and number 2 together. There's obviously a necessary sequence, but actually everything will settle within a clock cycle, and we're not overclocking things too fast. So by the end of our clock cycle, we can tell it to do both the things, and by the end, it will have read the memory. You can trust me on this because I'm a lecturer. So this brings us down to we've got phase 1, which is MAR from PC and read from memory at the same time, and then op from MDR. So actually, because number 1 and number 2 are both using the bus, we cannot do those two at the same time. So we need to have 2 distinct phases to our fetch, with the way that we're going to put this CPU together. Actually, the control unit is going to deal with with working out actually what needs to happen and sending signals to the right things in the right way. So all we need to do is to make sure that we send a couple of signals to the control unit, and we're going to call them fetch1 and fetch2. And we're going to have two separate input lines, one for fetch1, and that'll go high when we want fetch1 to happen. And then the second one is going to go high when we want fetch2 to happen. Okay, so after that, we need to carry out the instruction. And most of the instructions that we've got can be dealt with within one clock cycle. They don't need to do anything where you're separating things out time-wise. This is relatively, because we've got a pretty simple instruction set, and a very small number of them need to. And the ones that actually need to are the ones where we're dealing with the external memory, which is reading in data or writing out data. But we do need to accommodate the fact that we might need two here. So some control units go about this in a very different way, and they create a subsequence of events. So you've kind of got a little mini program that gets affected in hardware at this point, depending on what your instruction is, and it might go through over time a sequence of things. But we're going to deal with it by basically having two execute phases. And once again, we're going to do this by having two lines, one of which will be high for execute phase 1, and one of which will be high for execute phase 2. And so our instruction boils down to execute 1 and execute 2, and these are fed into the control unit, which will then work out what it's going to do in those two phases. Okay. And then finally, we're going to increment the PC. We're going to use a special modified register. I keep talking about this, but I'm not actually saying how it's modified. In fact, what it is two registers that are bound together with an extra piece of hardware which can add one. In some simulations, this is called, or possibly even in the hardware, these registers are called PC and Inc. And this is a fairly standard way of going about this. Inc only deals with PC, so I'm going to bind them together in our simulation in a macro, and there are going to be two phases for this. So the first phase is to copy PC to Inc via the adding one hardware, and then the second phase is to do the copy back again. So to copy Inc back to PC. When a jump has happened, then we'll deal with this in more detail later, but when a jump has happened, we need to not add one. And actually, we've got hardware already that can deal with this, so we'll reuse some of that stuff. So the program counter itself will actually handle the two phases. We're just going to give it two control lines, two execute lines, and we're going to call this increment 1 and increment 2. So here we go. That's the two phases that we need for incrementing the PC. So we've got a full set here of 6 things that we want to do to make our fetch execute increment happen. And we're going to, which are fetch 1, fetch 2, execute 1, execute 2, increment 1, and increment 2. And what we're going to do is we're going to make this a sequence of 6 lines, each of which is gets the signal one at a time. So only one of these lines is going to have a high on it at any particular time, and it's going to run through and generate the sequence and then go back to the beginning. So this is generated by a thing called a ring sequencer, which is actually a pretty straightforward thing to do. There are several ways of doing it. There are easier ways of doing it if you're doing hardware, and you can use the timing of the hardware involved. With our simulator, there are some problems with that, but we're actually going to, instead, we're going to use a binary counter linked to a decoder. And it's going to count up and give us out this sequence of discrete lines. So that's how we're going to make our fetch execute cycle work. We're actually going to do it by using these 6 discrete lines coming out of a ring sequencer. Each phase of fetch, execute, and increment has actually got 2 phases each. Some of this is, in particular, in terms of the execute. This is a little bit wasteful of time, but again, I don't really care. I'm sacrificing efficiency for the sake of simplicity here, which I keep doing. And there's always engineering choices to be made when you're designing something like this, and the needs of this particular CPU aren't really there in terms of efficiency or cost or size or anything like that. It's really about ease in making it and getting it up and working, and for the understanding of what's going on. So that's it from me for now.